I am completely discombobulated about time zones, but I'm going to stop my share so that whoever needs to get set up can get set up.
Hồ Chí Minh City is Thiện vé. Thiện có ghé ngang không vậy? Có ai you have seen ThienPhan hả, Nguyễn Văn Duyên hả? Nhưng mà Thiện bây giờ chắc không có lớp hả? Hình như nghe nói là có thể là mấy người tới lớp để gặp Thiện mà không biết có gặp Thiện chưa.
Mình có ok, hai phước
Không nghe rõ lắm Thiện đó hả? Hello Thiện. Vậy là vui rồi Thiện về đó. Đó thì Thiện được gặp dịp gặp Đà Nẵng, tiếc rằng không gặp Hà Nội, được gặp Đà Nẵng, Hồ Chí Minh City, chưa gặp Hà Nội. Chắc là Thiện phải lần sau về thêm một lần nữa. Nghe khó nghe quá, không có nghe rõ, không biết mọi người có nghe rõ không?
This meeting is being recorded.
Có thể nghe rõ anh Phước ơi.
Rồi giờ nghe rõ, giờ ra nghe rõ. Vậy chắc là ngồi xa cái mic quá đó. Hôm nay hình như ít người vào, giờ này mới 57 người.
Hôm nay là có bên Đại học Nghệ Tinh có tiếp đoàn của Ủy ban nhân dân thành phố Đà Nẵng ghé thăm, thì là có thăm cái phòng lab này. Đó cho anh kêu thì anh cứ diễn trên online nha, còn em sẽ chém gió ở offline nha.
Tức là học sinh không học hả? Hôm nay học sinh không học hả Sơn?
Các bạn vẫn học bình thường, anh vẫn giảng bình thường. Dạ.
Nhưng mà thấy 57 nhưng mà thật ra nhiều hơn hả hay sao?
Đây anh có thể thấy anh thấy các bạn sinh viên đây không?
Nhưng mà login vô chung hả? Login vô chung một tài khoản thành thử không thấy nhiều hả?
Dạ không tài khoản khác nhau anh, chỉ có máy chính ở lab là ấy thôi, máy chính của lab á, máy chính ở lab.
Okay.
Dạ.
Okay. Dave, you want anything to open before we go in?
No, I think we're ready to start.
Alrighty.
Yeah.
Let me share the screen. Sorry, I'm not prepared. Okay, I want to start with this. So, oops, it kind of messed up. But I wanted to start a person's request. We want to see what all the scores on all the assessment. So I just want to share the result. So basically, we started to collect since lecture 4. So we started to collect the points. So you can see it distributed from 40 to 150 over here. And go on to, sorry, the scale is not 100, but I normalize later. And then lecture 5, ranging from 35 to 100. And then lecture 6, 40 to 150. And 70%, 70 over 100. With this distribution going from very low to and then this is because of sorry for the lateness of the assessment for this lecture. We have this kind of distribution, but interestingly, the score is about 70% on average, with the exception of 83 and 85% here. Granted that all these questions are not meant to score the technical aspect of what you learn, but you really just to cover the knowledge before we coming in. So, but it's still an indication of we still have a few that either because of English or because of the lack of time to prepare, or different people at different time have score a lower score. But our goal is whoever have low score or don't understand fully, then the teaching staff is committed to help you, so that at the end you will be acquiring the absolutely necessary knowledge to complete this course with useful information and a newly acquired skill. So we are committed to identify whoever needs help. Right now, we don't have a really good way to, because we don't have real quizzes and real exams. So we'll rely on the local TA supporters, the teachers and the engineers who helping out the students at the labs. Will identify who needs help and really work hard in helping the people who didn't catch up as quickly as others, and with a goal of 100% graduation. So we just, the teaching staff just met and we set ourselves that goal. So hopefully we'll have good results. And starting from next week, after floor planning, we'll dig deep into placement and clock tree synthesis and routing. That's when the material become very deep for certain people. So it's critical that if you don't follow quickly enough, please let the teachers and TAs know so we can help you understand, so that you get something out of this course. So that's the message I want to share with you. And so if you need help, sorry, if you need help, please oh, this is the wrong one. Let your TA knows, and also ask questions, and also ask for help. Okay, so today we're going to go through the final part of floor planning, and originally we were going to cover all floor planning, but as we went through, it is apparent to us that power grid is very critical, and there are a lot of information, technical information about power grid, that I decided to use this lecture to cover more than what we have planned for. So hopefully this is useful for you, and the rest of them we can share later and they are straightforward enough that you don't need a teacher to tell you them, so you can read and watch. So today I'm going to went over how to build a power grid, right? How to build the core rings and the block rings, how to build straps. So what command to use and what the different definitions are, what the terminologies are, and some key concepts. Today, we're going to dig deep into power grid on the electrical side. So this is a complicated picture of what a power grid would look like. So you have the board where you have for chips that get the power from the outside. You have the supply voltage like a battery or whatever, and you have RLC networks, decoupling caps off chip. And then on chip, a simple circuit, a simple chip, it doesn't look like this. But say if you have a complicated circuit with a flip chip with a bump, so your off chip power will come in through the bumps, and then you have different areas. So you have a sleep mode in your part of the circuitries is active during sleep mode, and part of the circuitries are very active during functional mode, and you have some in sleep mode or stop mode. You have the different areas that are turned off by power gating, turn on, turn off, and then underneath you have the active regions. The power is drawn by active cells, and you have local decoupling caps. You have the local caps, and you have the ground grid underneath, and ground you have ground bars, etc. So this is just a visualization of what a power grid might look like in complicated chip with multi-VDD, multi-power voltage domain, etc. Just to give you an idea, not meant to confuse you anything, just to understand the scope of it. And one of the things you might hear about is the rush current. What is that? Rush current is very, very important for a power grid design. So rush current means that if you have a part of circuit, when you enter certain mode, you turn a switch on, and all the caps in that circuit will be filled with will be charged up. So when you do that, you need a lot of currents that go through that, and that's what we call rush current. So the power grid needs to be designed such a way that the rush current won't kill your chip because it's ground bounds, or because of the voltage drops that won't that create problems for the circuitry. Right? And on the active side, when everything is switching, you have voltage. So you see here voltage. If you look at the logic, is only one like VDD of in this case 1 point something. It's just a flat one, but in reality it looks like this because of the switching noise. You switch on and off, you see the charging and discharging of capacitors and all. And then the current will just go up and down, depending on when you actually switch it. A lot of circuitries, the current go up, and then when you not, it go down. So it looks like this, and you call them switching noise or supply noise, right? So the process of power planning, you have seen that we did all these building, but reality is an iteration, meaning that early on you haven't gone through placement and routing. You only have circuitries coming in from synthesis. So but you have to build all these power grid before you go on. So early on, you don't have a lot of visibility in terms of the actual switching, what transistors are switching, what size, what current. But you build based on certain estimation. So then you go through the power grid modeling is part of a tool that will analyze your floor planning view. It's not the final view. So that's why it's like early analysis. So you do the modeling of the power grid. You do an analysis that I go through and tell you what they are. And then you say, hey, the two most important things are IR drop and EM, right? So there are limits of what the maximum IR drops are, and there's limits of what the density requirement. So you analyze it and you say, is it within your limit? And if it is and if it is not, then you go back and fix it. You go back and change your power grid and do whatever decoupling caps, etc. So you fix it and then you go through again and again until you're done. That's when your power planning ends. So it's not just one-time deal, right? So then we have, like I mentioned, IR drop and EM are the two most important things that we look at. So on the topic of IR drop, so we already went through where are the sources of power dissipation. Power dissipation meaning that the power consumed by the circuitries. So we already learned the switching power. So switching power happens when a signal is switching inside the chip. So in this case, for example, the input here goes from 0 to 1. And so when it does that, there are a few components. One is called instance power. So you have a gate here. Inside the gate, you have transistors. So when they switch, then the transistor inside switch and charge and discharge the current, the internal volt capacitance here. So it consumes intrinsic power consumption for this guy, regardless of what happened outside of it. So it's called internal power. So that internal, we call energy. You read the Liberty file that you learn about. You see the power number in there. So the power number, the IR drop analysis tool will look at the number that I left, will multiply by the frequency of how fast this guy is switching and how often TR's toggle rate. So how often, what is the percentage of the entire operation that say 50% this guy will switch, or 20% or 30%. So those switching density or toggle rates will be calculated by the tool based on what you feed into the simulations. So a tool will calculate the power here, internal power, the instance power, and then that switching power also have a switching of the external wirings that this gate is driving. So include RC delay, RCs of the wire, and also the internal, the input. This is very small, but the input capacitance of the gates that drive it will drive multiple gates, and all those need to be calculated as the net power. So the net power is equal to, as we already covered in the last one, is like 1/2 of the capacitance times the V squared. This is squared, not 2. So the voltage square of the voltage times the frequency and times the toggle rate. So these two will make up this called switching. Made up the switching power. So this one, if you look at outside, it's going to be equal. Switching is equal to activity factor times frequency times effective capacitances. So you add up all these things and you time VDD square. So that's the switching power. But you see over here, there's a component of the switching power, dynamic power. We are talking about dynamic here. There are two types, dynamic and static. So dynamic have a switching power here, and also it has a short circuit component of it. Short circuit component is when you have an N and a P stack. When the input is changing, there are a period of time that both the N and the P are turned on. So there's a direct power consumption going from VDD to ground, right? So so that is what you call short circuit current. So short circuit power is equal to short circuit current times VDD and times the frequency of the operation, how often this input switching in 0 to 1 or 1 to 0. So that's a part of dynamic power. And then another source of power dissipation is static power. So static power mainly are power drawn when the internal circuitries are not switching at all. So when it's static, there are things that's leaking. So mainly is a gate leakage. You see the gate as the gate oxide is thinner. There's leakage between the gates. So different components of what really draining the current, the battery when nothing is switching. So this is very important in wireless applications, chips that goes into cell phones, go into handheld devices. So in addition to gate, you see I1, where's I1? I1 is over here. So this diffusion is say this is P substrate, this is N plus. So this junction have some leakage that go through. It's called reverse bias current. It's a diode current. And then I2 is what you call subthreshold current. Subthreshold current is when the voltage is below the threshold. There's some current that go through drain from drain to source. And also the I3 is over here. So this is gate induced drain leakage. It's part of the drain leakage, but it's induced by the gate voltages. And then we already mentioned I4 is gate oxide leakage. So gate oxide leakage is one of the major one. So as you can see here, it's different components of it. But you look at the overall, leakage power is a function of VDD, threshold voltage, and the width over length. So the more width, the more leakage. So the total active areas in the chip affect how leaky the chip is. So when you optimize for area, you optimize for leakage power as well. So this one, this graph show you how the leakage current progress over the year. This is 2020, and early on subthreshold and the gate leakage is low, but as you go smaller and smaller in gate length, the gate leakage and subthreshold become more and more dominant. And it exceeded dynamic in here, right? So dynamic is usually when you switch a lot, you consume a lot of power. But for smaller geometry, the leakage has become harder to deal with. So it's just something to be aware of. So it means that total power is dynamic power plus static power, and you over here, dynamic power is equal to switching power and short circuit power. So why we mention about power dynamic and static, because it affects what we call IR drop. So IR drop is one of the two most important factors, considerations when you design a power grid, and there's a reason why. So in here, when transistors are switching, so if you have the VDD coming from off chip and your internal circuitries are switching. When you switch, means you're charging a capacitance. So number one, input signal switch, like over here, you go from 1 to 0. So when you want, the P device is off. But when you switch to 0, P device turn on, it turns on, and then it charge the capacitance here to bring this node from 0 to 1. So charging this capacitor needs some power, needs some current. So the current go through to charge this capacitor. So when the current goes through, so wiring going toward this device have some resistance in the power grid. So the current go through, Ohm's law, right? I times R, that's a voltage drop. So if your typical voltage is 1.2 volts, but you have a 100 millivolts drop, then you only get 1.1 volt here. So as you know, the voltage, the VDD on a gate affects how fast or how slow the gate, the propagation delay is. So this is why managing the IR drop is important, because if this one is below the simulated worst case voltage, then you don't have a functional chip if your IR drop is not managed. So this is a just like illustration of what happens here. So when you switch over here, you see this is a signal, and this is the VD, and this is a VSS. So when the signal goes from 0 to 1, that means the reverse, from 0 to 1, no, this is the output. From signal to the input signal go from 1 to 0, you charging up. When you charge up the output, your voltage drop because of the IR drop, the VDD drops. But when you go 1 to 0, from 0 to 1, you're discharging this node to the ground. When a lot of circuitries discharging the node, it will create something called ground bounce. So if you have both voltage droop, they call droop is drooping down, and ground bounce, your effective voltage across this device is not VDD anymore, but is VDD minus ground. But in this case, VDD is below the VDD and ground is above ground. So your effective voltage across this device is much smaller than the typical. So this will have a direct impact on timing. So, and then static IR drop really related to leakages. So you when you analyze, you learn when you analyze IR drop, you first analyze with the static mode, and then you analyze with the dynamic mode. So static IR drop is really the drop that's caused by average power. The average power consists of leakage power, and consists of internal power and switching power, but on the average. Average meaning that that's over here. You see dynamic current can go high and can go low, but with the average is really averaging out along over time, right? So dynamic can go up and down. Average current is a number that just average values. But if you see here one frequency, if your frequency is slower, meaning that you only have this activity not very often, then your average power average current or power will be lower with the same dynamic current. So some of people confuse with static IR drop as just only leakage, and is a lot of you search online, a lot of people mistaken and say, static ion drop is really on leakage, but actually it's an average of internal power and switching power as well. But all these things, just for your reading, where the tool get our information from, mainly from the Liberty files and from the RC extracted files that tells you basically the capacitance that being charged and discharged. So I'm not going to go over here. You can read it, but basically static ion drop is equal to average current times the wire resistance, the equivalent power grid resistance. Is equal I average times R, or P average over VDD times R. And the different components of switching, leakage, and internal is already covered. So over here, one note is that, so this is very old, but it just show you that the leakage as the technology getting smaller. This is only 65, but technology getting smaller, the leakage become more bigger part of the whole power. So why we care about ion drop? So ion drop affects timing, and this is one of the example. So as you know, the delay through each gate is delays to each gate is dependent on the voltage that feed the gate. So depending where the gates are, the VDD go to these gates and VSS go to these gates are different. But in here, so if there's a critical path, timing critical path, and the cells that in the data path happens to have worse ion drops than other. If you have worse ion drop, that means VDDs that these guys seen is smaller than simulated. So that means the delays through this will be slower than normal. So if you see a slow data path, then you have timing problems if you don't take care of it. And so typically we have a limit of about 10% of ion drops. And as long as we guarantee that, then you can do worst case analysis, and you can guarantee that in any case the timing won't matter. So I mean the timing will be met if the VDD the IR drop is within certain limit. And then there's an example of that's on the data path. On the clock path, if because of IR drop sometimes can be if you have sometimes you have voltage troop, but sometimes you have also the spike on the VDD. But in this case, if IR drop is worse, then the clock is slower. When the clock is slower, then it affects the whole time, because as you know, whole time is the amount of time that the signal have to maintain the previous value. Don't change too soon because it will affect timing. But when the clock with the IR drop is lower, then your whole, if your signal changes too fast, then you have problems with whole time. So the whole thing is that oops. So yeah, so the key is it affects timing. So IR drops have an impact on timing. So that's about IR drop. Another components of another things of that power grid design have to pay attention to is electromigration. So what is electromigration? So it is defined as a gradual displacement of metal atoms in a semiconductor. So it happens when the current density is high enough to cause a drift of metal ions in the direction of the electron flow. In other words, if you have a current, very strong current over a wire, that electrons go go one way, the ions will create the metal atoms are moving over time, right? It can cause open circuits or short circuits. It can cause some kind of, so this is the atoms just move, and it can cause either of what we call a void. Void means it will create an open. The wires, when the atom move, it's no longer there's a hole here, or what they call hillock, is that some movement that will create a short. So when it moves out of the wiring, it touches the other wire. So that's a problem for why power grid, right? Because this relate to current density. If the wires is too small for the current that needs to go through it, that's when it happens. So these two, airdrop and electron migration, are the two serious issues that really need to be analyzed. And most of the time, people just over design the power grid and they don't do any simulations. They just say, okay, just put on the back of an envelope and calculate the overall power consumption and do some hand calculation of the total width of all the power grid that add together, and it has some rules in terms of electron migration. What is the maximum current density per unit area of the wires, and then it's done with it. But the problem with that is that to be good, you have to over design. But if you over design your power grid, you take away the resources for routing, and you make the chip bigger than normal, necessary. So your cost becomes a problem. So you need to be accurate in terms of analyzing all these phenomena, and to be accurate, you need some kind of accurate modeling, and this is just an introduction to how the power grid is seen and analyzed. So you see power grid, you have coring, you have local block rings, and you have straps or stripes, and you distribute the power over the entire chip to individual devices. So each individual device, an N and P transistor, in this case the P transistor getting power from VDD, is modeled as a current source, and the wiring leading to it is modeled with resistances. So over here is coming from the pad. You have different gates that draw in current at different locations. It's modeled as an R network and current taps network here. So it's mainly power grid resistance. You see from the cell, from the pad to the cell is really a resistance. And here is just more, the resistance is caused by when you have a route between, from VDD pad to a device, you go through different metal layers. In this case, for example, metal 5 is the top metal. It goes metal 5, and it goes through a via and go through metal 5, go through another via, go through metal 3. This is metal 1. So it go from 5 to 4 and to 1. So that means that 4 to 1, it just stack the vias, and it doesn't wire in metal 3 or metal 2. So this is the tool will extract all these R and C's, not just R's, and either it's wiring arcs or veer resistance. So, and over here, the current is called tap current. This is an average. This is static analysis. So an average current going here, this average current is a representation of a device that depends on width and length over here. So the tool will have all these models underneath to analyze the power grid. So what usually typically happen is during the floor planning, we do something called early rail analysis flow. Like I mentioned, a lot of times people just don't do this. They just do hand calculations. But for tough design, you need to do this. So you just learn about power planning. So after you power planning, you feed this into a tool like Voltus or Red Hawk SC or Prime Power, whatever, depending on the vendor. You get it in and it will analyze cost structure analysis. So it looks at your power grid and say, do you have, in a physical world, do you have missing vias? Do you have enough vias that cover the cross section of the two wide wires, or are there power grid but there's no via that connecting them? So they do a structure analysis so to point out the weakness in your power grid from the physical point of view, and then it goes through a power estimation. This is where your designer will say, okay, I want to analyze the grid to see if it can sustain the most power hungry applications. For example, in scan mode, when everything is switching at the same time, all the flip-flops are switching at the same time, everything happening, that's when we predict that there's a highest power consumption being drawn. So they do those simulations and they give you switching activities so that you can feed that switching activities into your circuitry to analyze the power. So because the power grid, as you see, is related to how much power, right? So how much power is being drawn when in certain operations of the chip. So when it's higher power, that it requires more robust grid. If you don't draw a lot of power, then you don't need that dense of a power grid, for example. So power consumption drives the power grid analysis, if you will. Right. So you do power estimation, power simulation first, and then either when what I just mentioned is when you already have the whole design that have everything. But in early on, you don't really have the implementation of certain things. So in here, you see the word power estimation and user-defined distribution, meaning that either I say in this area, this area is doing arithmetic logic unit, like do some calculation. I estimate is drawing about 0.5 amps. In here is a little bit random logic. I estimate these are standard cell areas. Estimate two amps. Actually, this is more than this. So it depends on the knowledge of a design. A designer can say, in this area, I'm estimating some numbers, some current drawn, and for this hard macro, I know this is a PLL, this is a ROM, whatever. So you have power estimation for these areas, and you feed it to the tool, right? So this is just an estimation, and sometimes you can feed in a p-square linear power distribution that is time dependent, etc. To make the story short, when you don't have the whole implementation, then you have models that you feed in the tool. And these models represent how much power is going to be drawn in this local grid. So then after you estimate all these things, then you do a static and IR drop and EM analysis. So static, you remember this is average power. So you run through the average power analysis and what are the static IR drop. So the static IR drop is lower than dynamic, but at least you know the quality of your grid in the static mode. So you have to make sure that the grid is robust enough to stand the static mode, the worst case power drop, IR drop of worst case static power, average power, because there's not a lot of things you can do to improve that other than just making sure that you have smaller devices and all. But the typical will be you need to meet the constraint on the static IR drop, and you need to meet the constraint on EM. EM is really a design rules. It's just a current density. So you do all these things and you make sure that the power grid is robust enough in terms of IR drop, right? In terms of it analyze what are the tap currents on the transistor. If it's too high, that it will highlight the hotspot for you. Like over here, say, hey, there's a lot of current being drawn in here, so you kind of address it from a static point of view, and say over here, there's so much power being drawn locally in this area, and the grid in here is too thin. It needs to be made wider, etc. So you do all these things first, and after that you do dynamic. So dynamic, as you see, it's just time-based instantaneous power and IR drop. So dynamic is analyzed, but fixing dynamic current problems involve a lot of things that you learn later. It's not the scope of this class, but there are different things that you can do, like decoupling caps, power gating, turning off and on, and all different ways of addressing and fixing. So you run dynamic, you see a problem that your IR drop is not within your limitations, and you want to fix them just like you fixing timing violations, right? So you don't analyze and say, oh, that's it. You analyze and you go back and forth to optimize and fix them, including moving cells around, moving power hungry cells around. Just to dynamic is really a lot of times are local. So if you manage the current congestion, then you can fix the dynamic issues. So yeah.
So we had a question come in. A student noted
Okay.
That we only have formula for static IR drop in the slide. So does that mean that we only calculate static IR drop beforehand, and the only way we know about the dynamic drop is testing? Is there a range for the tolerance of static IR drop value, or is it needed to be extremely accurate?
Thanks for question. That's a good question. The formula is really for some estimation, but both static and dynamic IR drop cannot be calculated by hand. So static IR drop. So when you this is the early rail, but the sign off IR drop analysis involve power simulations that will involve the simulations with the test cases and the test patterns that represent the very high power consumption mode for the chip. And after you've done that, you with the same input, you calculate the static IR drop and you calculate the dynamic IR drop. So static IR drops really calculated. Where is it? I don't have a.
Hey Phil, I will
Yeah.
cover the early power analysis for both static and dynamic in placement. So after in the placement lesson.
Oh, really?
Yeah.
That's good. That's awesome. So basically the same picture. Let me see, trying to find it. Yeah, over here. So, oh, so in here, the same simulations depend on the speed. The average current is calculated from the dynamic current. So it's not like a number. These numbers are just an estimate, but the actual average current and power are calculated based on the patterns. So it's tool-based, right? So I hope I answered that question. Oh, there's some more question here. Yeah, so the tolerance really, you specify what is your target worst case, what is your worst case IR drop. So basically, when you run this analysis, you already know you already have your target. You already have your target. Okay. When you know a violation, meaning that, hey, my IR drop cannot drop below 10%, for example. If you have 0.9 volt typical voltage of typical operations, and you say, I am simulating the worst case, I'm signing off the timing at 10% below 0.9. That means I assume the worst case on all the transistors will be 0.81. That means 0.9 minus 10%. 0.81 volt. I guarantee any transistor in this chip will not be below 0.81. So if I can guarantee the chip is fast enough with that voltage, then I'm good. So now to guarantee that, you do this analysis not early, but the real power drop analysis. And if you see any IR drops is greater than 90 millivolts, then you will have to fix it. So, but you don't do hand calculations. It's all a very sophisticated tool that helps you come up with all these numbers.
All right, Phil, we had a couple of questions come in a lot while you were answering this one. How do we actually examine these phenomena in the real world? Or do we just use a tool that does simulated calculations? Is the first one.
Okay, so good question. So oops, I keep on hitting the wrong button. So you see here, this is your examining the problem. You have opened your circuit doesn't work, and you get it under the microscope. So this is an actual picture, right? It have that. So that's the electron migration. In the IR drop, means your circuit is not functional, meaning that it doesn't operate at the speed you want it. So for example, if you do 1.2 gigahertz on an Apple chip, and under the worst case operating conditions, it won't operate at 1.2 gigahertz, and your application require it to be 1.2 gigahertz. So when you run the clock at 1.2 gigahertz, you get garbage, meaning the chip won't work. You play the video, yeah, it won't work. So that's the effect on the on power grid is really in terms of timing, performances. Yeah.
All right. The next
So,
question to come in is in
yeah.
the pre-assessment, it said that the dynamic IR drop is more critical than the static IR drop. Why is that?
Both of them are critical. So static IR drop, but the dynamic determines whether or not you pass or fail. So the static, if you meet a requirement on static, you have better chance of meeting the requirements on dynamic, because there are things on dynamic that you can fix, like the coupling caps. I don't know if I have that covered. The coupling cap is, maybe I should talk about it a little bit. So a lot of these power consumption, the hotspot. So, oh, I haven't done this one yet. Okay. How come I missed this? So this is an example. This one example. So when you run all those circuit analysis or IR drop analysis, you have some people mistakenly say this is a thermal map. This is not a thermal map. This is an IR drop map, color coded, meaning that when it's red, usually depending on how you cover it over here, there's some range that you can specify. The worst will be red. It could be the worst case, or could be a violation, depending on what you label it. So say, for example, for here, say red is more than 10% of your target. So you can see, usually your power path are on the outside. So you will, in your simulation, you can say, okay, here's my power tap at this location, at this location, at this location. And usually the IR drops become worse and worse, further and further away from the taps. So you have some blue, green, and orange, yellow, red. So in here, it indicates that this is, in this region, your IR drop is worse than your simulation. So you need to fix them, for example. So the color, the map, the IR drop map, help you visualize where the problem is. And you can say, okay, oh, this is where I'm doing my FFT. So maybe I should spread the thing out, or maybe I can increase the grid here to be wider. So if you have power grid wider, then the resistance is lower. The resistance is lower, than IR drop is lower, right? Because it's IR. So these are the things that will help you visualize where your problems are in terms of IR drop. All right, so in here, see abrupt IR drop color change, right? From this color to the other color. I mean, there is maybe power grid here is not continuous here. So you can zoom in and say, hey, what can I do to improve the power grid here? Or in here, they say these RAM, these are connected well to the power grid, therefore they're not red. And but these RAMs are further away, or maybe they need to be improved, etc. So that's one analysis. Which way I should go? In here, the tool will help you with the color here. Say, hey, there's a this graph, this display doesn't look at IR drop, but it looks at current. So current density, right? So it say, hey, there's a very high current density here. IR drop might not be a problem, might be, but it will help you visualize this, and you can zoom in and say, oh, sure enough, this power grid over here is so thin, right? And then what is this one? This one is another example of IR drop. So you can play with the color code. This is 14 millivolt, and then from 0, that means no IR drop, to 10, 20. So it will show you. By this one, you can tell that there's a current tap here, maybe there's a tap here, there's some problem here. So it just help you visualize. And over here, that show the differences, just illustrate the relationship between static and dynamic. Meaning with the same simulations, you have static. So you pay attention to the static first. You fix the static, but dynamic is something on top of that. And here in this example, you see there's a 17 millivolts increase in IR drop. Yeah. Obviously, because this one look at the instantaneous versus the other one look at the average. So,
All right, Phil.
yeah.
Yeah, I'm assuming you just finished that last question. We have one more.
Yeah.
Why is high current density is the primary cause of electromigration in metal lines within a power grid?
Yeah, because that's the nature of it. So maybe can I delay the previous one? I forgot what the previous question is, but since we haven't covered this, I want to cover this, and I'll get to that question. Over here is just highlighting the whole thing. There's a high IR drop. So this is an example. There are a ton of stuff that you can do to address IR drop, but this is one simple example. Say your analysis gave you a red, and all you need to do is just adding additional, metal lines in this grid, and you do it again, and you don't see a red. So the tool helps you. Just there's no way you can calculate by hand. So. Yeah, and then the question related to electromigration is simply because of the definition of it, right? So if you recall, the electromigration, what causes it? It's like when you have electron go in, when the current go in one way, with the electron moving, it's just physical that it will move some atoms of the metals. It's just over time, over a period of time. Just as an atom, the physics on the metal, it just move the atom because the current keep on going, it will move. And it will move, then it causes this kind of phenomena we call opens and short. So it's really the definition of electromigration is really about current density, right? Because if you're so dense, then they will move the metal atoms, or in here they call it iron. So, but if it's not so dense, then it won't move. Just simple physics. So but the good news is it's really easy to fix because all you need to do is reduce the current or increase the size of the metal, right? So it's a density or decrease the current, meaning that you can move. So if you have a group of circuitries drawn a lot of current in this region, then you move that circuitry outside or far away, then the density on the local wire will be fixed. And the question, can we predict the impact of EM, and if it occurs dramatically in our design, how we can handle it? The answer is tools. You need to run tools. Yeah, so when you run all these analysis with the inputs and the operating conditions and what it runs, your chip runs, the tool will tell you if you have a problem, right? The tool will tell you if you have IR drop. The tool will tell you if you have current congestion, current density, and you have violations. So you run, and And this is power grid, but also on signal. It's called signal EM. You have signal that can draw a lot of current. You have a big buffer driving some wires, thin wires. You have a current density problems. So you use a tool to help you identify where you're violating the EM rules. Yeah. So you sort of design to avoid it, but you use a tool to tell you how bad it is and tell you to fix it.
Yeah,
All
and Joe,
right.
let me add a little bit more.
Yeah.
So the
Sure.
tool uses information from a technology, right? If you use, for example, 90 nanometers versus 30 nanometers, the EMs, the EM thresholds are different per wires, right? So different technology will have the wire, you know, let's say metal 2, metal 3 could be 2 micron or 0.2 micron, depends. So it's already pre-characterized those, and then there's EM libraries which the tool uses, so it knows, you know, what is the limit for those wires. And based on the information, when you do power analysis and IR drop, and depending on how much power is coming in, where it's coming from, and the distance, so it will know based on the pre-characterized data, it will know exactly what's the violations. That's how we flag it and give you the maps, and then you go back and fix it.
Yeah, thank you. But so yeah, so those limits come from the fab, and it's also layer dependent. So you have current density limit on, you know, different layers with different values, right? So keep in mind the width is not the only thing here. This the thickness of the metal too. The thicker it is, the bigger cross section. So this is current density is really about the you know, it will be impacted by the cross section as well, because yeah, so good point. But those are limits coming from the foundry, and they are design rules. So you in the past you don't run them, people don't run them, but to do it correctly, especially with very high power, high performance chips, you cannot afford not to run all these analysis, because you will have a problem. All right, thank you for all the questions. I appreciate it, Dave. I think probably we need to have 5-minute break.
All right, I'll get a clock started, everyone. We'll see you at about 5 minutes.
Okay, Thien, are you gonna cover the lab, or you want me to cover the lab?